Welcome to the 1.2 online lesson where I'm going to cover two main topics that you can see, and they are tree diagrams and the fundamental counting principle. So let's get started here. We had a menu on the previous video where we talked a little bit, but today we'll talk about, let's say today's breakfast, a little more sophisticated. This time you can order a drink, milk or juice, a meat choice, ham, bacon, or sausage, and eggs. And let's just say that when you order that you must pick one of each. And so here we go. Let's start with drinks. When I take a look at the drink options, okay, we'll really have two drink options here. I can choose milk or I can choose juice. So once I look at that, I have milk or juice. And when I start my tree diagram, I need to use that and realize there are two options. There are two kind of roads I could travel. I could go the milk route or I could go the juice route, and that's kind of the main idea. So what happens here is I start to form this tree diagram where I begin this road. I have to make a decision. Do I go down the milk road or do I go around the juice road? And that's the beginning of my tree diagram. Which one will I choose? And once I make that choice, let's say I just happen to choose milk, then I move on in this road, and the next path I have to choose is which type of meat I'd like to order, and there are three choices. So there are going to be three bars or three lines that come off of the milk choice because there are three options after I pick milk. And the options will be I could choose milk and then ham, or milk and then bacon, or milk and then sausage. Okay. Now, if I would have chosen juice, I would have the same three options down here. I could have a ham, bacon, or sausage as my options for meat choices. So my tree diagram starts to look like this. And if I'm just going to order a drink and a meat order, there's 6 things that I could do, 6 total outcomes here. I could have the milk ham, milk bacon, milk sausage, or I could have juice ham, juice bacon, or juice sausage. There's 6 total outcomes. But in this case, I'm supposed to now order eggs. I can order them scrambled or fried. So if I ordered milk and then ham, now I need to make a choice. 2 options, either scrambled or fried. There's going to be 2 lines coming off of here because I could choose scrambled or fried. And that's actually going to happen for every one of these. Now I also shortened a lot of things here because you'll see this in tree diagrams. M for milk, J for juice. Milk, H for ham, milk ham, then I can order scrambled or fried. Now notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different things that I could order if I were to look at how many total orders could I place with this menu. There are 12 total different orders that I could place here. This is a nice tree diagram that shows them all and all the possible things that I could order. So if I were to just draw a path here, let's see if you could figure out what I ordered. That is one path of all of the 12 that represents the order where I ordered juice, bacon, and scrambled eggs. That's the order that it shows right there. All right, moving on though. Tree diagrams can get really, really big, especially if you think about a real menu. What if I had 7 drink choices and 5 meat choices and maybe 3 egg choices and a dessert? Maybe there's 10 dessert choices. There's a lot of options. I'm really not interested in drawing that large of a tree diagram. So what we can do is this thing called the fundamental counting principle. Now remember, today's lesson, there's 2 main things. Thing 1 is tree diagrams, and we just covered that, and there's the example we just did here on the screen. And the second main thing today is the fundamental counting principle. Fundamental counting principle just says this: instead of drawing this huge tree diagram, I am going to ask myself, how many drink options were there? It was milk and juice, so there were 2 drink options. So I have 2 drink options, and after I pick one, I'm then going to have 3 meat options, and after I pick one of those, then I have 2 options for how I would like my eggs cooked. The fundamental counting principle says if I want to know how many total ways there are here, in this case there's 12 listed in the tree diagram, I actually can take 2 choices times 3 choices, which is 6, times two choices, and I can get the number 12. Rather than drawing the huge tree diagram, I can just figure out that there's 2 options times 3 options times 2 options. There's a total of 12 things that could happen. That's the fundamental counting principle. It just says, hey, I could just multiply these numbers and get the number 12 rather than draw this huge tree diagram all the time. So it's helpful. It's another way to quickly calculate sometimes. So let's take a look at another scenario. Mr. Henderson, that's me. I have 3 children in my family. Let's talk about what could have happened as far as my children. Okay, now my first child that I had, he's a son, he's a boy. So what occurred in my family is my first child was a boy. Now we know that it could have been a girl. I'm just going to go with boy for now. The next outcome, my second child, was a girl. I'm actually, we have boy, girl here also. Go back here. So let's go back. My first child's born. The doctor's going to tell me, hey, it's a boy, or the doctor's going to say, hey, it's a girl. Well, in my family, the first child was a boy. Second child comes along. The doctor could have told me, hey, it's a boy, or could tell me, hey, it's a girl. My second child's a girl. But if I want to look at what were all of the things that could have happened with 3 children, I could have a boy or a girl the first time. If I had a girl the first time, it's possible that the second child now would be a boy or girl. Now this is just 2 children. By the way, if there are 2 children in my family, there's 4 things that could occur. They could both be boys. We could have first boy, then girl. We could have first girl, then boy. Or we could have 2 girls. If there are 3 children, like in my family and like this problem is stating, then I need to go another step. For the third child, we need to add this boy or girl outcome. Boy or girl outcome for each of these steps. Now right now I'm drawing the tree diagram, and that's topic number 1 for the day, drawing tree diagrams. And we can see there are 1, 2, 3, 4, 5, 6, 7, 8 different outcomes. 8 outcomes. Now it just so happens in my family first was boy, then girl, then the third child was a boy. Can you see that outcome, boy, girl, boy, in the chart? Because my family is listed in this path on the tree diagram. Boy, girl, boy. That's what occurred in my family. There are many other things that could have occurred in my family. Now that's tree diagramming. But remember, there's this thing called the fundamental counting principle that says, you know what, if I just want to know how many ways that could happen, there's a faster way. Child number 1. There are 2 outcomes there, boy or girl. So remember, we're writing how many outcomes. Child number 2. There's 2 outcomes, boy or a girl. Child number 3 comes along. There are 2 outcomes, boy or a girl. Okay, and fundamental counting principle says if you multiply those numbers, you will get 2 times 2 is 4 times 2 is 8. It says there are 8 ways that could occur. That's exactly what our tree diagram found. There are 8 ends on that tree diagram. And that's what the fundamental counting principle does. It says how many things could happen. Rather than drawing the big tree diagram, how many things could occur. Now, the fundamental counting principle is much more likely to be used when we talk about real-life problems. For example, Minnesota license plates. Here's an example right here. It's 3 letters and then 3 numbers. If I ask you to list the sample space, I'm telling you to list every single license plate that's possible in the state of Minnesota. That might take you a while because you're going to start with AAA 001. And then you're going to have to go AAA 002. And AAA 003, 004. You're going to keep going, and then when you're done with all those, you're going to have to go AAB 001. It's going to take a little while. This is not something I really feel like doing right now. So the next step would be, hey, maybe draw a tree diagram. And if I'm going to draw a tree diagram, I'm going to look at the first slot here. And the first slot is a letter. So my tree diagram is going to ask the question, how many different letters are there to choose from? There are 26 letters, which means I'd actually have to physically draw 26 lines here in my tree diagram. That's going to take a little while. Now that just would take care of the first letter. What a mess. Not going to do it that way. The fundamental counting principle is much, much better. It says, hey, you know what? I'm going to kind of list off these slots. I have a letter, 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 followed by a number, number, number. And the fundamental counting principle just says, hey, how many different letters are there to choose here? There's 26 letters in the alphabet. How many letters to choose here? 26 letters again. 26 letters to choose from. How many numbers can I choose for this first digit? Now, think 1 through 9, but then also the number 0. So there's actually 10 digits that could go here. 1 through 9 and the number 0. There's 10 digits to choose from for each of these. And the fundamental counting principle says, if you want to know how many ways you can do this, you would just multiply all of those numbers. So you'd take out your calculator, probably, because this is going to be a pretty big number, and you multiply 26 times 26 times 26 times 10 times 10 times 10, and it is definitely a large number, and that number that you'll get looks like 1757600. That is a large number, 17,576,000 different license plates. That's a lot. Okay, so that's just an example of where fundamental counting principle would be much more beneficial than a tree diagram or trying to list them all by hand. All right, so moving on. Take a look at this. I have 4 books, and here's just kind of a series of books that I read a year ago. And I'm going to order these books. I just want to know how many different ways could I take these 4 books and just kind of put them on the shelf. Now I could put them in the order that they're sitting. That's possible if I just set them here in order. Okay, that's one way to do it. But we know that there are a lot of other ways to organize books. I could switch these 2 around if I wanted to. But the question is, how many different ways could I display these if I were going to display these on a shelf, maybe in a store, or on my shelf in my room, I guess, for that matter. How many different ways can that be done? Well, here's how you do it. You ask yourself, how many books could I choose for this first position? So I'm going to take these books and drag these off again. And the question is, how many books are there to choose from to put right here in this first slot? And right now, before I even do anything, there are 4 books to choose from. So there's 4 choices for this slot. Okay, I need to pick one. So I'll pick a book. Maybe it happens to be this one. Okay, and I'll put it in here in the first slot. Okay, now the question is, how many choices are there for the second book? Well, there's only 3 left over, so now I have 3 choices for this one. I'll pick a book, slide it over. Maybe that goes in the second slot. How many are left? And maybe you've noticed a pattern now. And I'll finish this off. There's 2 books left, and when I put 1 underneath here, there'll only be 1 left here. If I want to know how many ways I can organize these books, it's going to be 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is 24. There are 24 ways to organize 4 things visually. And that again is the fundamental counting principle, because it tells me there are 4 options for the first slot. And once I put something there, there are 3 options, and then 2, and then 1. And I would just multiply. So, moving on, almost done, so hang in there. How about this game? There's a game where I roll a 6-sided die. If I get a 6, I get to roll again. If I don't get a 6, I have to flip a coin. Now, this is going to be a larger tree diagram, because right away I have 6 outcomes that I could have. So I roll the die, and there are 6 things that could happen. I could get a 1, get a 2, a 3, a 4, a 5, or a 6. Okay. If I roll a 1, I have to flip a coin. That means I've got a heads or a tails option. If I roll a 2, I flip a coin. Heads or a tails option. 3, flip a coin. 4, flip a coin. 5, flip a coin. 6, if I roll a 6, I have to roll again. 1, 2, 3, 4, 5, 6. So there are 6 things coming off of this, because when I roll again, I could get any of these numbers again. This tree diagram looks different. It is slightly different. Okay, that's just kind of a rough, quick problem there for you to take a look at. All right, so that kind of wraps up the online part of this lesson. How many outcomes are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's actually 16 outcomes here in this little game. We'll talk about this kind of stuff